Thank you very much. Actually, it was very lucky that Bill gave the lecture before me, because he already told you several times that several things that I actually wanted to introduce, so that will make my life easier. So what is the problem that I want to address? So this is the following problem. From now on, I will have a Riemannian manifold M, which is supposed to be smooth and compact and connected. Well, connected maybe I don't even need. It does not have any boundary. And the dimension is any dimension. And the problem that I'm interested in is to understand whether in this Riemannian manifold there is a non-trivial minimal hypersurface embedded. So, question, is there a non-trivial embedded, oops, yeah, here we go. That was the mistake that I shouldn't have to make, right? Oh, okay, great. Undo. Okay, great. Maybe I can use actually this fancy device and cancel. Right. Embedded minimal hypersurface. So as Bill already pointed out, in the lowest, in the least possible dimension, that this would be two-dimensional Riemannian manifolds, the question is whether there exists a non-trivial closed geodesic in the Riemannian manifold. So he already showed you if the topology of the manifold is non-trivial, if the pi one is non-trivial, then you can minimize length in a certain homotopy plus, and you find. It's much harder to say, or it's much harder to prove that there is a non-trivial geodesic if the manifold is topologically trivial. So the same actually happens in the higher dimensional situation. So in the higher dimensional situations, of course, going to be much more complicated, but nonetheless, if the homology of the manifold is non-trivial, then you actually can minimize in an homology class, and there's an established theory for doing that. This is called the theory of currents. So for us, the interesting situation is something like M equal to the standard sphere. So the easiest compact manifold on which we don't have a minimizing property to show that there are non-trivial minimal surfaces, right? So if we take any surface and we try to minimize in its homotopy class or homology class, since that is trivial, we're going to end up with a point. So the test case for us is always going to be M equal to the n-dimensional sphere. Okay, so as it was already said by Bill, this problem was settled by Birkhoff in the sort of list dimensional situation that is for two-dimensional surfaces, right? So the answer is actually always yes. And there is this famous work of Birkhoff in 1917. If you want to come to minimal hypersurfaces, you have to wait much more. So notice that I've said actually embedded. If I had said immersed, then there would be also other literature to cite. I will tell you in a second. But if you care about embedded minimal hypersurface, then the first result is actually in the 1980, and this is a monograph of Pitts. And the answer is yes, but this time the dimension of the manifold, so let's say the dimension of the manifold, maybe it's better to set it actually to be n plus 1. In such a way that the minimal surface has dimension n, then in this case, this is true for n less or equal than 5. This would be Pitts. Okay, and then Schoen and Simon actually handled any dimension slightly later. So this is actually 1981. Okay, with a caveat. In fact, the Schoen and Simon theorem is going to show you that there are minimal hypersurfaces which are non-trivial, but they might have some singularities. On the other hand, I don't want to enter into the detail of that, because This is a phenomenon which already happens when you are actually looking at minimizing hypersurfaces. For instance, there's a famous phenomenon which tells you that already when you look at the plateau problem, if you're looking for minimizing hypersurfaces sufficiently high in the dimension, there are going to be singularities. In particular, singularities appear when n is bigger or equal than 7. So there might be singularities, but this is not going to bother us. Let us think that we are actually for in the lower dimensional case, and then I don't have to be over technical, right? Okay, these singularities, though, for n bigger or equal than 7 are very, very mild. Okay, so, well, the question is therefore settled. But one of the sort of awkward points of this proof of Pitts is that it's an entire book. It's a pretty complicated proof. And what I'm going to tell you today is actually how you can make this proof much more manageable. In fact, I have published a paper which is just a simple paper. Well, simple, of course, modulo that you have to assume several other things in the literature, but let's say, fairly stated, if you assume the same amount of things that actually Pitts assumes in its monograph, you can actually get away with this paper of mine and a PhD student of mine that is called Tasnadi. So that's actually from 2009, and it's going to be published soon. So simple proof, some 20 pages. Okay, as it was already presented by Bill, actually the main argument of this proof is going to be a min-max argument. So we're going actually to set up a sort of framework which is similar to the Birkhoff approach for curves in two-dimensional Riemannian manifolds. And let me not go into the details of what we have done or what other people have done. I mean, there is actually, what I'm going to show you is actually the sedimentation of the ideas of several people. Let me just tell you what is in fact the proof. Then later on, when we maybe go into the details, I will tell you who introduced this and that idea. So let me tell you actually the framework which we use in our paper and which works. So first of all, what we do understand as a sweep out of an m-dimensional manifold. So we take actually the point of view that we are looking at surfaces which are boundary of open subsets. So a sweep out of my ambient manifold M is a collection of open subsets of M which depends on this parameter 0, 1. And this omega, I mean, this collection of open subsets have several properties. So let me list the properties, which are here. So first of all, the first subset is the empty set, and the final subset is the entire manifold. Then there is a sort of continuous dependence of these subsets on the parameter t. So the first obvious continuous dependence is that actually, if I look at the symmetric difference between omega t and omega s, right? So the volume of this is actually converging to 0 as s approaches t. So this tells you that the volume actually of omega t is continuous in the parameter. But I want, in fact, more properties, and I want actually to say that essentially the boundary of these open sets, they depend smoothly on t. But I can't quite say that. Actually, one of the problems is that I have to introduce point singularities. So this is going to be sort of the most important continuity property. So let us give it actually a C, a name. So for every parameter t, I will be able to identify a finite number of points p. So this is actually a subset of M, a finite subset. So this is a finite subset of points which are exceptional. If a point P is not in this big P, then omega s, the boundary of omega s, intersect a ball of radius, of small radius, intersected P, depends smoothly on S. At least if S belongs to some small interval centered on T. Okay, so this is my sweep out.
Little p is in capital P or not in capital P?
Right, not, sorry. Otherwise it wouldn't, yeah, thank you very much. So capital P is actually the set of exceptional points, very good point. Outside of them, I have the continuity properties. And there, somehow, the things might be singular. Okay, this is not quite the end of the story. I will also ask another very small thing, that is that the total area of the boundary of my set omega is actually bounded. So, around the exceptional points, I'm not going to have exceedingly large area. So, this is the final requirement. Let us maybe call it sort of B. Yeah. So the n-dimensional volume. Oops. Edit. Undo. Oh no, I changed actually. Edit. Undo. Undo. Right. So the n-dimensional volume of the boundary of omega t is always less than plus infinity, and in fact it depends continuously on t. Also. Okay, now I'm all set, and what I'm going to do is I'm going to actually set up the min-max problem, which eventually will lead to the existence of an area, of a non-trivial embedded minimal surface. So let us first define what is the min-max problem. So the min-max problem is simply the following. For every sweep out, say omega t, I actually define f of omega t to be the maximal volume that I have in the family for the boundary of the set. And then my min-max problem is going to actually look at the infimum of all f of omega t among all sweep outs. Okay, and what in fact I claim is the following. So the main theorem, which is actually the theorem of Pitts, Schoen, and Simon, and for which we have this sort of new short proof, is in fact the following. So, well, first of all, m0 of m is obviously bigger than 0. This is actually quite trivial to prove, that we'll see. And then there exists a sequence of sweep outs maybe I should use actually another thing. So this would be okay. And a sequence of slices in the sweep out. So a sequence of parameters tk, such that the following holds. The boundaries of the tk surfaces are converging in a certain sense, which I will specify in a moment, to a smooth minima surface sigma. with total volume which is equal to m0 of m. Well, and in fact, these slices are almost maximal. So in fact, I should also write that this m0 of m is in fact going to be the limit of the f of the omega tk. Oops, this is not going to be good. Let us cancel it actually. Let us write it over here. No, that was bad. Right. So it's going actually to be the limit of the f of omega k, omega tk. So meaning that this sequence of sweep out is actually a minimizing sequence of sweep out for the energy f. Okay, so this omega k, I mean this boundary of omega k tk is what we call a min-max sequence. So you could think about it as the sequence of maximal slices in the sweep outs omega tk. For some technical reason, you cannot exactly pick up the sequence of maximal slices. It might be that you have to pick up a nearby sequence, but this is just a technical problem. Okay, so in which sense actually I have this convergence, and in which sense is this sigma smooth? So this sigma is smooth in the sense of any normal person if the dimension n is less or equal than 6. Otherwise, it might have singularities, and let us not bother about that. I mean, if you want details, I can tell you exactly what are the singularities that can occur, or what are the things that are known about the singularities that can occur. But it's more interesting actually to understand in which sense I have the convergence, because the convergence is in a rather weak sense, unfortunately, and this is something on which we are in some other problems actually working, because it would be nice to have a much nicer notion of convergence. So first of all, let me tell you that in fact sigma might occur with some multiplicity. So sigma is in fact going to be the union of finitely many connected components which might occur with some multiplicity though. So actually I cannot exclude, for instance, that sigma is a double cover of a sphere. That might happen. Okay, the convergence is the so-called varifold convergence. And now let me just tell you very briefly what is the varifold convergence. Well, what is a varifold? A varifold is the following idea. So you have your surface, and you attach. Okay, so this surface is in your ambient manifold, which in this moment is just a piece of Rn. So this is sigma, which is staying in a piece of Rn plus 1. Okay, I actually consider two different measures. So the first measure is the volume measure restricted to sigma, meaning if I want to measure what is the measure of a certain subset of Rn plus 1, I just intersect with the surface, and I compute the measure of the intersection. So this defines a measure. So this measure I denote it this way. So this is the first measure. Okay, I'm not actually going to say that the varifold is this measure. I'm actually going to say that the varifold is a measure in the Grassmannian of Rn, in the Grassmannian of n-dimensional unoriented planes. So on this Grassmannian, I actually put the following measure. So let me just use the following notation. So, and I will explain it in a second. Okay, so here I have my surface, and I'm just thinking that I have a fiber bundle. So at every point of Rn plus 1, I attach the Grassmannian of n-dimensional planes at that point, and I pick up the tangent to a point x in sigma. So this is going to be my Tx of sigma. And now I construct a measure on this fiber space. And the measure is simply going to have on the base, as base measure, this volume measure on the surface sigma. And on the fighter, I put a Dirac mass at every tangent point, at every tangent space. Okay? So if you have a flat plane, then it's strictly a product measure in the obvious coordinates, right? If you have a surface like that, you can always think anyhow that it's going to be a product measure if you change coordinates accordingly on the Grassmannian. Okay, and now once I have defined, okay, so this in technical words, this is the varifold measure induced by a smooth surface. Now, a general varifold is going to be a measure on the Grassmannian of Rn plus 1, on this fiber bundle, which is non-negative, and which to each fiber is actually a probability measure. Okay? So the convergence in the sense of measures, meaning that if I attach the obvious measure to the surface's boundary of omega k tk and the obvious measure to the limiting surface sigma, that is weak convergence when I test with continuous functions. So let me just summarize it maybe in this way. General varifolds are measures on the Grassmannian of n-planes, of unoriented n-planes of M. And the varifold convergence is the convergence of measures. Okay, so why actually do we have to use such a strange convergence? Well, this convergence has some obvious advantages and some, well, there's actually a very little, small one obvious advantage. That is, it is actually compact. I mean, it's a compact space. So I take an arbitrary sequence of surfaces. As soon as I actually bound the area, this sequence of surfaces is converging to some object over there. On the other hand, this space sucks, because there's so many actually objects in there that if you want to understand whether the object in there is a smooth minimum surface, you're going to suffer a lot. Okay, that is actually what makes the book of Pitts a book with a lot of prerequisites, and what still makes actually our paper quite hard paper to read, in fact. On the other hand, there are some reasons for which you actually are bound to use this type of convergence, at least at the beginning. So, of course, there is always the hope that you could prove actually a better type of convergence for the surfaces a posteriori, and that is what we are working on. But one of the feelings is that, at least at a certain level, you have to swallow some kind of, bad stuff like that. And why are we using, for instance, varifolds and not some other notion of convergence? So, for instance, one could ask, okay, you have your set, right? This is omega k tk. This is maybe converging to some set, and there are actually very good theories about how to close open sets which have a perimeter on which you have a bound. So why aren't you actually taking the limit of the sets? And the reason is that there is a possible situation which I don't know how to rule, and actually nobody knows how to rule, and which might occur in this convergence, and which seems very unlikely to occur when you are looking at these min-max arguments. But on the other hand, it's apparently an extremely difficult problem to prove that it does not occur. So, in principle, what my sequence of surfaces might do, and I'm not able to exclude, is that it might do something like this. You see, it might, so imagine this is a sphere. So there is an inner sphere, and here there is a neck, and there is an outer sphere. And so this, this you can see it as the boundary of a subset in R3, which is going to be sort of the subset which is contained between these two spheres, essentially, right? Now, what I cannot exclude is that my sequence omega k tk which is converging to my sigma looks like this, with a smaller and smaller neck, and the two spheres which are collapsing, the outer and inner sphere which are collapsing. Now, these guys, in my varifold sense, they converge to two copies of the sphere, but the sets converge to a set of measure 0. right? Because the set gets squeezed between the two spheres and the volume goes to 0. So in the usual notion of convergence of sets, the set disappears and the boundaries do not. And unfortunately, since that might happen, if something like that happens, I cannot exclude that when I look at convergence of sets, I actually end up with the empty minimal surface, which is exactly the thing that I didn't want to have from the very beginning. So now, this looks like a very pathological example. On the other hand, it gives you an idea of why the proofs are more complicated than usual, right? I mean, when you actually are looking for minimizer of something, there's the big advantage that you can make global changes on your surface. You say, okay, hell, if this were the minimizer of something, I could try simply to cut along the neck and throw away one of the two spheres, right? And make a competitor. But remember, this is coming from a family of surfaces which are having some continuity in the parameter t. As soon as I know what to do on some surface, I also have to know how to modify the whole family of surfaces in between, which means that if I'm going to make a local change on my surface, I might hope of making this local change even on the surfaces nearby, and then let maybe my perturbation go to 0, and then, for surfaces which are far away, I don't do anything. But if I'm going to do such a type of global change, it might be extremely difficult to understand how to modify the rest of the family. Right. Okay, so first of all, let me actually advocate a little bit the work that I have done together with my PhD students. So, for instance, one of the nice things that I can do is that, first of all, I could state a theorem without sort of going through 20 or 30 pages of notation, which would be the book of bits. I can also show you some things for which it actually requires a hell of a lot of work, and for which I have very, very simple proofs of 2 lines. So first proof, of course, first thing, of course, that you have to worry about is there any sweep out in your manifold? You are actually in a very general setting, right? So to find a minimum of this function f, you need your class to be not empty. So that option, actually, this is also, the example that I'm going to give you in a second, which is the proposition why the set of sweep outs is unempty. It's also going to justify why we introduce these singular points P. Actually, there are various reasons for introducing these singular points P, but one of the reasons will pop out in a moment, and I will actually tell you that though this sort of definition of sweep out looks extremely complicated, it's in fact not that complicated. It's quite intuitive. And these singular points that I have introduced are actually quite needed in the theory. You cannot do without them. So proposition. Take a Morse function. Okay, take the level sets of the Morse function. Then this is a sweep out. Probably I cheated because I told you that omega 1 has to be the entire manifold, right? Omega 1 is going to be the entire manifold minus few points. Let's say that these singular points might be there. So omega t is a sweep out. That's it. So the subset of sweep outs is actually empty because on any compact manifold, in any compact smooth manifold, there's always a Morse function. Okay, so why is that actually happening? Well, obviously, if you take a level set of a function and you are out of the critical points of the function, then the level sets are actually behaving nicely, right? They are smooth, embedded manifolds, and they are depending smoothly on the parameter t. So the set of points P is in fact going to be the set of critical points of the Morse function. This is actually it's like whatever page, whatever on Miller, very easy. The set of critical points of a Morse function is finite. And if you're worried about the fact that the total boundary of these level, of the boundary of these level sets, this has to have a finite perimeter, you have to study a little bit how the Morse function is behaving along the singularities. Huh? But believe me that that's not a big deal. So that's the first proposition. So the proof, in fact, I'm not going to write. It's too easy. Second proposition, obviously, m0 of m, that was the beep. Perfect. So the second proposition, that is m0 of m, is in fact positive. Why? Well, he already gave the proof, in fact. Omega t is depending smoothly. There's a t which has half of the volume of the manifold. Apply the isoperimetric inequality, the boundary of this omega t has to be bigger than some given constant. So this is just proof. Simply pick omega t, or if you want, omega t0, t naught, such that the volume of omega t naught is equal half of the volume of m, and use isoperimetric inequality. So remember, the f of omega t has to be bigger than the volume of the boundary of omega t0, and the boundary of omega t0 is bigger than some constant, which depends only now at this point from the volume of the manifold and the isoperimetric constant of the manifold. Okay, that's it. Now, why is this thing actually converging? I mean, why actually this min-max argument is converging to a minima surface? So sort of sketch of the proof of the theorem, of the regularity, if you want. Well, whatever, I mean, what already actually came out from the lecture of Bill is that if you could use a gradient flow for the functional that you're looking at, which is the area functional, and if you had all sorts of nice properties for this gradient flow, that is smooth evolutions and so on, you would actually apply this gradient flow to a sweep out to say that, okay, let us flow all the surfaces in the sweep out with this gradient flow. If I don't, I mean, if this gradient flow never meets the critical points, all the sweep outs will actually be sort of shrinked to 0. The energy will decrease more and more until I get close to 0. And that is obviously a contradiction to the previous theorem, to the previous proposition. So ideally, we would like actually to use a gradient flow. Well, but that, of course, is the ideal world. In fact, it does not work. Nobody so far has figured out how to use a gradient flow approach actually to make this argument work, right? And the biggest problem is that, well, first of all, the mean curvature flow, we know actually it creates singularities. It creates, in this case, it creates also singularities which are essentially unavoidable, right? I mean, as soon as you get out of the convex realm, it does create singularities. In general, it's not even clear, and this is in fact probably what Bill is going to clarify in the next lectures. So far, it was not even clear that what sort of generic singularity would be. Okay, now we could hope for having maybe a proof of how the generic singularities look. There still would be a hell of a lot of work to do to apply this idea over there. So, what in fact one could use. On the other hand, if you go back somehow at the time of Birkhoff was able to run actually his argument without having the gradient flow. So one could suspect that actually you could be able to run the argument even without the gradient flow. Okay, so one first thing that you could do actually, that you could give to your advanced graduate student as an exercise in functional analysis is to prove that in some very weak sense, in this varifold convergence, the surfaces are converging to what is called the stationary varifold. What is a stationary varifold? It's a sort of weak solution of the minima surface equation. So it's a sort of generalized notion. I don't want to actually bother you with that. This would be extremely technical. But let us say that it's not difficult to do that. So it's not difficult to show that there is not a gradient flow, but there is a sort of flow which is continuous and is shortening these surfaces if at least you don't have a stationary varifold with the correct, say, area. Though for stationary varifold, this is called mass. So this leads to the existence of a sort of weak solution. what we could call a weak minima surface. Now, in a half ideal world, the weak solutions of some decent elliptic partial differential equations, like the minima surface equation, are smooth. But now, one of the real catches of the subject in which I work, which is geometric measure theory, is that it is really extremely far from any kind of ideal world you might imagine, even half. So this notion of weak minima surface, which would be the stationary variable, unfortunately is known to be non-smooth. There are a hell of a lot of non-smooth examples. So one obvious non-smooth example would be, for instance, the intersection of two hyperplanes. That's something which is actually even a smooth immersed minima surface. But for us that are looking at embedded ones, that's not good. Okay, so this actually is what creates really a lot of troubles, and what you want to go actually beyond that is you have to understand a little bit more what you can do. I mean, a weak notion of being a minima surface is not enough. Okay, so what you can actually bring into the game is something more. You can actually argue using some stability for this surface. Now, this is going to be tricky because we are actually trying to find a minima surface which is unstable, right? We know that. On the other hand, if you look at the basic examples, right, what you are picking up with these one-dimensional sweep-outs are saddle points which have at most one direction which is negative. So think about, for instance, the typical example that Bill gave, right? So the equatorial sphere that you pick up with these sort of sweep-outs. Now, the equatorial sphere is not stable, but on the other hand, the Morse index is not that bad. Okay, you take out the nullity, the Morse index is actually 1. Now, this actually suggests you that in some sense you can try to show that you are not only a weak minima surface, you're actually a stable minima surface. At least on small subsets of M. Maybe not globally, but on a local level. So, local stability is actually the key idea to get regularity. Okay, in fact, the key idea, which is already, which already appears in the book of Pitts, and in some sense the sort of heart of the matter of our proof is not really something that I can touch, because the key idea is how to actually, for the key of our work was how actually to manage all these ideas together in such a way that you get a proof which you can read in some sense, which is manageable, which is as short as possible. But the key idea is that actually the surfaces which are converging to my min-max surface are almost minimizing surface. And so this is actually the sort of notion which actually can get you around these weak minima surfaces, which are stationary points of the area functional, and actually allow you to use some area minimizing property, which is a much stronger property, some local minimality property. Okay, so what is an almost minimizing surface? Okay, so an almost minimizing surface, so there will be an epsilon. It's actually an epsilon almost minimizing surface. So this is a surface sigma such that if I want to deform it continuously to a surface which has much less energy, much less area, I actually have to go during my path a little bit up. So for every one parameter family of deformations of sigma, so let us say continuous deformation of sigma, if the volume of sigma 0, if the volume of sigma 1, that is the final surface, is less or equal than the volume of sigma, which would be the volume of sigma 0, minus this epsilon, then somewhere along the path, the volume was actually larger than the volume of sigma 0 plus epsilon divided by 8. Okay, that's the end. So, check it out. What actually happens is that even your unstable critical points of the area functional that you are actually trying to catch with these min-max arguments, on sufficiently small open sets, they do have this property. Okay, so that's in some sense the key idea of this business. In fact, this key idea was introduced back a long time ago by Almgren, and in some sense the history of the problem up to now has been on how to actually manage to use this key idea together with the analytic tools that one has in order to prove the regularity of this minima surface over there. Okay, so thank you very much. That's it. Yeah. Sorry? No. Somehow it's a number, and we don't even know how much is this number large. Of course, you can, okay, so you can give an obvious bound, but that would be trivial. I mean, there's an obvious bound would be that if you have a general Riemannian manifold, the minimal surface cannot have a too small area, right? So that would give you an obvious bound. But apart from this bound, which is sort of trivial, you don't have any other, I don't know of any other way of bounding that.
How did the stability figure in? So you started with stability and then you talked about the almost minimizing property?
Okay, so now it fills in the following way. So how the proof works in a sort of, this is really very, very, very sketchy outline. So your surface it has this almost, actually, this is an epsilon almost minimizing property. Actually, what you prove is that your sequence is epsilon k almost minimizing for some epsilon k which goes to 0. Now, take an open set U on which you have this epsilon k almost minimality property going to 0, and actually replace your surface with the one that you can connect to your original surface without going more than epsilon k divided by 8. So in some sense, so take this definition and sort of define a variational problem, which is I look at all surfaces which I can connect with it, with a compact supportly perturbation, and I look at the minimizer. Now, it's not easy, but you can prove that this is actually a smooth minima surface. This guy is a smooth minima surface. Now, this guy not only is a smooth minima surface, it's stable. Because, true, it's not a minimum, but it's a local minimum. Okay, now you've got you got what we call a replacement inside. Well, now you've got a sequence of minima surfaces which are stable. I use the stability estimates shown in Simon, and this converges to a stable minima surface in the limit. Now, the catch would be to try to show that this limiting minima surface actually coincides with the original surface, right? Because you have modified this guy over here. Well, there are two reasons for believing that you modified this guy over here only, and still the limiting modification is the same minima surface. One of the reasons is that your epsilon almost minimizing, so you shouldn't have changed your surface so much. This is a sort of weak reason. The strong reason is that there ought to be some kind of unique continuation, right? So the global surface was this stationary varifold, and now you know that you're still a stationary varifold, but somewhere you're a minimal surface which is smooth. Now, of course, if you have two minimal surfaces which coincide out of a compact set, convex set, they have to be equal because of unique continuation. Now, this is the ideal world. So for stationary varifolds, actually, this property is false. But you can still get around it. So it's still a basic unique continuation argument.